Hello. In this session, we're going to look at how we can study filters using the Seelab device. And the electrical filter that I've chosen for this particular demo is a multiple feedback bandpass filter that I've constructed on this board, and it uses a single op-amp, couple of resistors and two capacitors to form a small bandpass filter. So let's get started. First, I'm going to open the filter characteristics experiment, which will show you the schematic diagram for this multiple feedback bandpass filter. So as you can see, this has first off, for characterization, you have a signal input, which is your waveform generator WG, and that is also simultaneously provided to the A2 input for monitoring the input characteristics. Now this goes into your feedback circuit, your bandpass filter circuit, starting with R1, which is a 10K resistor, R2, which is a 1K resistor to ground. There are a couple of capacitors, 0.1 microfarad and 0.01 microfarad, and a feedback resistor, which is 100K. Now the output is monitored using A1. Now, as you can see, the values shown here, A1, A2, are amplitude values. Now the amplitude is extracted from this sinusoidal signal, and that is done from the plot. So let's switch to the plot view. And as you can see here, you have this, the black trace representing A1, which is your output from the filter, and the red trace, which will be fairly consistent throughout the experiment, which represents the input given to the filter. Now let's see what happens when you change the frequency. So let's start from a small frequency. Let's say 150 Hertz. You see the black trace is smaller. The output is smaller than the input. Now, as you keep increasing the frequency, at around 600 Hertz, both have the same amplitude, right? Let's keep increasing it. You see, beyond 600, it's reducing again, which tells us that the peak of this bandpass filter lies somewhere around 600 Hertz. Now, coming back to this amplitude here, let's extract it from the graph. So if you want to get these values, you simply select a region in the graph. This performs a sine fitting routine on both these graphs and sends the data across to these two labels here, which show you what the amplitude is. You can also look at other parameters by clicking here, and you can see phase differences and other things. So right now we're only interested in the amplitude. So let's just select amplitude for both of them. Okay. So this is a sort of interactive mode where you can manually set different frequencies. If you want to set a precise frequency, you can tap on this and say, okay, I want exactly, I don't know, 500 Hertz. And it'll tell you, okay, fine, we've set 500 Hertz. But if you want to get the filter characteristics graph and also look at maybe the phase relationship as you sweep different frequencies, you would need to go to the record data tab. So here I have record data next to this. And here we can set what is the starting value of the frequency, what is the stopping value, and the step size. So since we already figured out that the peak is at around 600, we can, let's say, start from 50 Hertz and go to maybe 1200 Hertz. In steps of maybe 10 Hertz would be appropriate, right? So let us now initiate the characterization. So for that, you just click on the start button, which will set frequencies starting from 50, then 60 Hertz, 70, so on to 1200 Hertz. And for each of these frequencies, it will extract the amplitude for both the signals as well as the phase difference and plot. So as you can see, at around 600 Hertz, you get a peak. So this is the time domain data here, and this is your frequency versus amplitude, and the secondary axis is frequency versus phase. Now, if you were to look at where the peak is, see that? So at this peak, you can clearly see the phase shift is 180. So you can observe that the phase flips around the peak of a bandpass filter. So that covers your bandpass filter characteristics. Now, the other things that you can see in this experiment or in this menu at the top right, you can mark it as complete, which basically takes a screenshot of your results and saves it to a PDF. You can also add additional tools if you wanted to maybe tweak and use different types of filters. So you can share stuff. There is an online documentation which takes you to a slightly more detailed setup. on how you can do this experiment. There's also some Python code to do the same thing with the desktop application and by writing some Python. There's also a simulator, but this actually shows a different filter. It shows just a small tank circuit, but you have many options here and you can pick out whatever circuit you want to design, and you can characterize it, because for characterization all you need is a signal input, which is your sine wave input, and you need to monitor the signal that you're providing to the input just to make sure that it's consistent, and that's given to the A2 oscilloscope input, and the output of the filter is measured by A1. And on the leftmost tab you have help, which is the built-in help, which is available for every experiment that you have on the Seelab application. And finally, maybe we can run this again with a smaller step size and conclude the video. So just go and start this experiment. So you can see that it's going to start sweeping for different values. And this is your previous data set. So you see, initially there are a few bad data points. This happens because the sign fitting routine needs at least like a full cycle before it can finally figure out what the frequency is. So when your frequency is very small and your time base across this is fixed, it basically has only a partial, part of this whole waveform when it captures, and that can create small, errors. But as you can see, when you take a second set of data points, the frequency response curve will overlap what we just found out with your higher step size. So you can see that the output waveform is slowly growing, and it will keep growing till it hits the peak resonant of this bandpass filter, and then it will start dropping. So you can see your phase shift here. When you observe phase shift at the peak, the phase shift is now going to invert. So I think we can stop now. Thank you.